Hello students, and welcome back to the Quarantine Lectures. So today in 1.4, which is our final of the mechanics series, I want to go through some sample problems of problems that you will see quite frequently in your statics courses. Hey guys, so today we're going to be talking about a very common problem you're going to see in your statics courses, and that is of the seesaw, right? The seesaw problem is a very good basic problem to study static equilibrium, and that's why you're going to see it a lot. So what we see here is a typical seesaw, right? It's literally just like the things you used to play with on the playground, right? We have one mass on one side, we have another mass on the other side, we have a fulcrum in the middle, which is the balance point, and it's going to swing back and forth based on those weights, how far they are apart, right? Remember back to our torque and levers discussion. Okay, now there are going to be a lot of variations on this problem. Where should the fulcrum be placed to make it balanced? How far from the fulcrum should each weight be placed to make it balanced? Given some amount of info, determine the mass of the board, because that also can affect, right? If you have the super heavy board, it may not matter as much where the weights are. And then if a third mass is added, where should it be placed to make it balanced? So fundamentally, all of these are just variations on the problem, given different information. Find the ultimate solution, which is how to make this thing balance. Okay. Now, what's interesting is there's actually two methods to solve these type of problem, and both methods are actually fundamentally the same with what we're trying to do. So first, let's do a quick review of static equilibrium, right? In static equilibrium, the sum of all forces has to equal 0, right? That's x, y, z, and that means that the torque has to equal 0, right? A force of 0 means there's no acceleration, which means there's no movement, right? This is the foundational concept of statics, right? We had already talked about that actually in class. So with this, we see the seesaw here, right? But I've drawn in forces, right? The down force of gravity from mass 1, and the weight of 1, and then the weight of 2, the down force from gravity of 2, each side, on the forces on each side of the fulcrum have to be the same. Now that doesn't necessarily mean they have to be the same distance, because in this case, they actually can't be the same distance because they're potentially different weights, right? So what you just have to do is just a static equilibrium. You just have to balance the weights on each side using your lever equation. All right, then we also can go back to episode 1.2 or lecture 1.2, and we can discuss the concept of toppling, right? Remember, we were looking at center of mass there. We could find the center of mass of an object, and if that center of mass was ever to cross over the outside point, we would get toppling. Now, in the case of a fulcrum, you only have one exact point. If the center of mass is on either side of that fulcrum, you are going to get toppling. The seesaw is going to move in either direction. Right, so fundamentally what we can do is we make sure that the center of mass is exactly over the fulcrum, right? We place the fulcrum at the center of mass. So that's another method by which we can go through this, is we find the center of mass of the fulcrum, or of the seesaw itself, of the seesaw object, and we place the fulcrum there. Both solution methods are fundamentally the same. So what we're going to do now is we're going to go through a series of problems. I'm actually going to talk it out, and we'll go through them. The first problem we're going to go through is fulcrum placement. So a 10 Newton weight and a 15 Newton weight sit on opposite sides of a beam. Where should the fulcrum be placed in order to reach static equilibrium? All right, students, so in this problem, we have a 10 Newton weight and a 15 Newton weight that are 10 meters apart, and we're being asked to decide where to put the fulcrum at in order to make this seesaw balanced. So what we're going to do for this problem is we're going to use the center of mass method, meaning that we are going to make sure that the center of mass of this combined object is where we put the fulcrum. So to find the center of mass here, what we're simply going to do is use our equation. So center of mass equals, let's put the reference here at 0, and here would then thus be 10. So the center of mass is going to be 10 newtons times 0 meters plus 15 newtons times 10 meters, divided, of course, by the total mass, or in this case, the total weights, 25 newtons, which is of course the 10 plus the 15. In fact, let's just do it that way, 10 plus 15. Show our full work here. Okay, so we have our center of mass equals 0 plus 150 Newton meters divided by 25 Newton meters. So our center of mass is at 6, right? Because our Newton meters cancel. 150 divided by 25 equals 6. So our center of mass here would be 6, which means that in this problem, we should be putting our fulcrum at 6 meters away from 10 and 4 meters away from the 15. The second problem we're going to look at today is balancing weight. A 30 Newton weight sits on a balance beam 2 meters away from the fulcrum. We now have a 50 Newton weight, but we need to know where it should be placed in order to reach static equilibrium. Hello students. So in this problem, and another seesaw problem, in this case what we have is a 30 Newton mass, or 30 Newton weight, that has been put 2 meters away from the fulcrum. And we're being asked to decide how far away the 50 Newton needs to be placed in order to balance this seesaw, right? So in this case, let's use the lever method. Okay, so in this case, we want to make sure that the forces are balanced. So using our lever arm, we then have 30 newtons times 2 meters away. And now we have 50 newtons times x, which is also meters away. So in this case, we have 60 Newton meters equals 50 newtons times x. And we just simply solve for x here. And what we get is 60 over 50 Newton meters, and this one is just newtons. So the units cancel, we get 1.2 meters equals x. So what this means functionally is that the 50 Newton weight would need to be placed 1.2 meters away from the fulcrum. In problem 3, our final problem today is adding a third weight. So we have a 30 Newton weight and a 20 Newton weight sitting on a balance beam, each 2 meters away from the fulcrum. Now we of course know that that is thus not balanced because we have the same distance but different weights. So what we're going to do is we're going to add an additional 20 Newton weight, but we need to know where it needs to be placed in order to reach static equilibrium. All right, students, now in this problem, the third type, what we have is we have 2 weights that are on a seesaw. We know how far they are from the fulcrum, and what you can see is this is a 30 Newton at 2 and a 20 Newton at 2, which means that 2 meters away, of course, which means that this seesaw is not balanced. So what we're being asked is if we were to add another 20 Newton weight to the seesaw on this side, how far away would it need to be? Okay. So in this case, what we want to do, of course, is use our lever method, knowing that, of course, in static equilibrium, both sides are matched. So let's do 30 newtons times 2 meters, because that's the 30 Newton weight, 2 meters away from the fulcrum, so the lever there. And now we have 20 newtons times 2 meters, this guy, plus 20 newtons times x. And all we now have to do really here is just solve for x. So now we have 40 Newton meters plus 20 newtons times x. We have 60 Newton meters here. 20 Newton meters equals, because we of course brought this to the other side, 20 Newton meters now equals 20 newtons times x. And we find that 1 meter, canceling these guys, equals x. So what this means is that this 20 Newton weight should be added at 1 meter away. All right, guys, so those are our 3 example problems for today. Now, what you may have noticed when we were going through these was how fundamentally simple they were, right? There wasn't complicated math. It was very simple and straightforward on how to solve these. And that's what's so great about these type of problems, and that's why you're going to see a lot of them, is because it's a very simple and straightforward way to look at static equilibrium. You're looking at torque, you're looking at forces, you're looking at center of mass, you're looking at balancing, and you're making sure that all the forces are balanced. So that is going to be it. This will cap off our mechanics string. I hope you've been enjoying the quarantined lectures, and I hope you'll continue to join us in the future. Thanks for watching.